The topic of my talk will be at the crossroads of three areas. One is 2D statistical mechanics, another is graph embeddings, and the third is integrable system. The relations between 2D statistical mechanics and graph embeddings and between 2D statistical mechanics and integrable systems are fairly classical. But the connection between graph embeddings and integrable systems is more recent. More specifically in this talk, I will describe a correspondence between, on the one hand, the Dimer model, which is a statistical mechanical model for random perfect matchings on graphs, and on the other hand, circle patterns, which are some graph embeddings corresponding to, let's say, collections of circles with combinatorially prescribed intersections. And under this correspondence, I'm going to identify two local moves. One local move for the Dimer model called the urban renewal, and one local move for the circle patterns called the Michael move, based on a classical theorem of planar geometry called Michael's theorem. And both these local moves are going to generate some integrable dynamical system. So the first part, let me describe the Dimer model. The setting is the following. You start with a graph, some vertices connected by edges, and you define a Dimer covering to be a subset of edges of the graph, such that each vertex in the graph is adjacent to exactly one edge in the subset. So here, for example, you have these three blue edges which form a Dimer covering of the graph, because each vertex lies exactly on one blue edge. And a Dimer is by definition one of these blue edges. So this graph has three Dimer coverings, and the Dimer model is a study of random Dimer coverings. So we want to put a probability measure on the space of Dimer coverings. So one very natural probability measure is the uniform measure, but actually we're going to consider more general measures. And for this, we're going to consider an extended setting. The setting is first a graph, but also edge weights, meaning that every edge carries a positive real number. And we are going to associate to each Dimer covering a weight, which is given by the product of the weights of the edges involved in the Dimer covering. For example, for this Dimer covering, you have an edge with weight C, an edge with weight D, and an edge with weight E, so you have weight CDE. And then we define a probability measure associated with these weights. This is called a Boltzmann probability measure. As follows, you draw at random a configuration with probability proportional to its weight. So for example, you will get that configuration with probability CDE divided by the sum of these three weights. So this sum, by the way, is called, the normalizing constant is called the partition function of the model. It's an important quantity in statistical mechanics. So this model was initially introduced in the 1930s to study the adsorption of diatomic molecules at the interface between, with a crystal surface. And it's also known, quite well known in the computer science community, this model under the name of perfect matchings, because you can interpret a Dimer covering as a matching of each vertex with exactly one neighbor. So this model in general is difficult to solve. What would we like to know? We would like to compute, for example, the partition function, and we would like to compute the edge correlations. If you have a general graph, these questions are very hard to solve. But they become tractable if you restrict yourself to planar graphs. In that case, there were some techniques developed by the physicists in the 1960s that allowed to solve the model exactly. So from now on, our setting will be planar graphs that are additionally bipartite. Bipartite means that I can color the vertices of the graph in black and white, such that each edge has exactly one white endpoint and one black endpoint. Or to put it differently, white vertices only have black neighbors and white vertices only have white neighbors. Another way to define bipartite graph is to say that every cycle has even length in the graph. And also in the setting, we will have positive edge weights. So what we actually care about for such a graph is not so much the edge weights in themselves, but the Boltzmann probability measure that they induce. Note that if for this white vertex here, I multiply all the edge weights for the edges incident to it by 2, then whenever I have a dimer covering, it will contain exactly one of these 3 edges, so its weight is going to be multiplied by 2. So by this operation, I'm multiplying by 2 the weight of every dimer covering, so I'm not changing the probability measure. So more generally, we can consider gauge transformations, which consist in picking a vertex and multiplying by some positive number the weights of all the edges incident to that vertex, and this is not going to change the underlying probability measure. So what we actually care about is not the collection of edge weights, but the collection of edge weights quotiented out by gauge transformations. 2 collections of edge weights are said to be gauge equivalent if we can go from one to another by a sequence of gauge transformations. And we actually have some coordinates on the space of edge weights modular gauge. These are given by certain face weights. So whenever you have a face, for example, this square face, you can take the alternating product of the edge weights. So you turn around the face in a counterclockwise order, and when you go from a black vertex to a white vertex, like here, you put the corresponding weight in the numerator, and when you go from a white vertex to a black vertex, you put the corresponding weight in the denominator. So here you have for these 2 faces, you have these 2 variables, which we call capital X variables. And these variables are indeed gauge invariant, because if I multiply by 2, for example, these edge weights, then I'll have 2f in the numerator and 2d in the denominator, which will cancel out. And these provide us with coordinates on that space. And you can also look at the outer face if you want. So how did the physicists solve this model in the planar case? It's by the introduction of an object called the Castellane matrix. So we start with a graph, planar graph, bipartite graph with positive edge weights, and we are going to construct a matrix. But actually, before we can construct this matrix, we need some additional information. And this additional information is called Castellane signs. What is this? It's an assignment of some signs to each edge I'm going to assign one sign, plus or minus, in such a way that if I look around a face of degree 4, or multiple of 4 in general, then there will be an odd number of minus signs. For example, you see around this face, there is exactly 1 minus. And if I look around a face of degree 2, 6, or more generally, a face of degree 2 modulo 4, there is an even number of minus signs. So as Arvind said, you can look at the outer face, which has degree 6, and it only has plus signs, so an even number of minus signs. And then once you choose Castellane signs, you can construct the Castellane matrix K to be the weighted signed adjacency matrix. The rows of this matrix are indexed by white vertices, and the columns are indexed by black vertices. So how do you get the entries? For example, the entry 1, 1. You look at white vertex number 1 and black vertex number 1. They are connected by an edge, which has edge weight C and Castellane sign plus, so you multiply these two, and you get a C in position 1, 1. In position 2, 2, between black vertex 2 and white vertex 2, you have an edge with weight D and Castellane sign minus, so you put a minus D. In position 1, 3, why do you have a 0? Because white vertex 1 is not connected directly by an edge to black vertex 3. So that's why you have a 0. So these are the most classical Castellane signs, plus or minus. We can actually consider a more general version. Consider complex Castellane signs. Instead of just having plus 1 or minus 1, we can consider assigning any unit complex number to these edges. And the constraint this time becomes that if you take the alternating product around the face of these complex signs, then this alternating product should be equal to plus 1 if the face is of degree 2 modulo 4, and should be equal to minus 1 if the face has a degree multiple of 4. So for example here, for this square, You go here, you have 1 divided by I times 1 divided by I. That's minus 1. So it's consistent with this minus 1 here. Yes, it's always possible to do that. And again, you see K is the weighted sign adjacency matrix. So once you compute, so this Castellane matrix K is not a deterministic function of the original positive edge weights. It depends also on the complex Castellane signs or on the real Castellane signs, but whatever matrix you get, in the end, if you take the absolute value of its determinant, it will give you the partition function. And you will get the dimer correlations by looking at certain appropriate minors of the inverse of this matrix. These are classical results in the 60s obtained by Castellane, Temperley, and Fisher. So the classical way of thinking about these Castellane signs is the following. These edge weights and the Castellane signs. We classically think that the physically relevant information are the positive edge weights. Because if you just increase one positive edge weight and maintain all the other edge weights fixed, then the probability that this edge carries a dimer increases. And on the other hand, we consider that the Castellane signs, whether complex or real, are just some algebraic trick that allow for these results to work, but don't have directly a physical meaning. There's another approach to this, a more modern approach, which is to merge the complex Castellane signs with the positive edge weights. You multiply them out. So instead of having 2 things above each edge, you just have 1. And that's just the entries of the Castellane matrix that I had. And in some nice cases, these complex edge weights carry some geometric interpretation. And we will precisely see that in the case of the correspondence between dimers and circle patterns, these complex edge weights will have a geometric interpretation in terms of circle patterns. And here you can also take the alternating product around each face of these complex edge weights. So if you do that, you can separate this alternating product into 2. First, the alternating product of the signs. Because of the condition defining the complex Castellane signs, these signs will be either +1 or -1, depending on whether the face is of degree 0 or 2 modulo 4. And on the other hand, you will have the positive edge weights, which will give you, as an alternating product, the positive x variables. So in the end, this alternating product of complex edge weights is just plus or minus the positive x variable. So this was, I think the timer was not set. Okay. Right. So this was the dimer model. Now let me tell you about a different story about circle patterns and circle centers. So circle patterns are an object that come from discrete differential geometry. They were quite well studied, where they arise as discretizations of conformal maps. So the definition for a circle pattern is the following. You start with a planar graph G. So for me, a planar graph is just some combinatorial data. I have a set of vertices. I have the adjacency relations, which vertex is adjacent to which vertex. And I also have around each vertex the cyclic ordering in which I see its neighbors. So it's just a purely combinatorial information. It doesn't have a specific embedding. It's a graph which is embeddable in the plane, but I'm not looking for the moment at a specific embedding. Then a circle pattern for G, it's a map from the vertex set of the planar graph G to the plane. So it's a way to draw this planar graph in the plane in such a way that there is, for each face, a circle going through all the vertices around that face. So let me say a disclaimer that for now, let's forget about what happens at the boundary. There's a boundary face, but I'm not looking at a circle around the boundary face. And there will be issues with the boundary, but for 10 minutes, let's say, let's forget about the boundary issues and just focus at what happens in the bulk. So this is a way to draw the graph, but this drawing, in the way I did it here, was an embedding, but more generally, we don't have to consider embeddings of G. The edges may cross. So isoradiographs are circle patterns where all the radii are supposed to be equal. So it's a special case. And actually, there is some correspondence between isoradiographs and diamond models, and the correspondence I'm going to describe generalizes this correspondence. Once you have a drawing for the vertices of G in the way of a circle pattern, you also have a way to place naturally each dual vertex of G. So what is when you have a graph G, you have a notion of duograph. You place a dual vertex inside each face of the primal graph, and you connect two dual vertices whenever the corresponding two faces are adjacent. And then you can just place each dual vertex. Each dual vertex corresponds to a face, and each face here corresponds to a circle. You place this dual vertex at the center of the circle. And so you have a way to draw naturally the duograph in the plane. And if you forget about the drawing of the original graph, of the primal graph, you will get what I will call circle centers for G. So this is less information. When I had the circle pattern, I had both the centers and the radii for each circle. Here I only have the centers. And you can ask the question, if I just give you this picture, can you recover the circles just from this picture? If not, it would mean maybe that there are several circle patterns that have the same center. How many circle patterns are there which have the same centers? Other question, suppose I just give you the drawing of the duograph. I don't tell you that this drawing comes from a circle pattern, comes from centers of a circle pattern. I just give you an arbitrary drawing of the duograph. Does it come from centers of a circle pattern? If not, what are the conditions on an arbitrary drawing of a duograph to say that it comes from a circle pattern? And again, the drawing that I'm considering right now, the drawings of the duograph, are not necessarily embeddings. The dual edges may cross for now. So I'm going to answer all these questions in the case when the graph G is bipartite. So we're going to consider some animation in GeoGebra, which involves this bipartite graph. It's a portion of the square grid. Okay, so here you have a circle pattern with the combinatorics of a portion of the square grid. And you can observe the following thing. Look at these two vertices. They are adjacent in the graph, and there's an edge connecting them, and this edge separates two faces, and each of these faces corresponds to one circle. If you draw the line connecting the two circle centers, then this black vertex is obtained by reflecting this white vertex across the line connecting the two centers, just because they are the two intersection points of two circles. This means that if in your circle pattern you know all the centers and you know the position of one vertex, then you can deduce the position of every other vertex. Just because once you know one vertex, you can reflect across a line connecting centers and you get all the neighbors. So now suppose you know only the centers. How can you pick the position of this initial white vertex, which you can then reflect? The answer is actually that you can pick this white vertex to be anywhere. Wherever you pick, you place this white vertex, you can then reflect and get a circle pattern. This means that there is a two real parameter family of circle patterns with given circle centers. Now, let's observe another property of these circle patterns. Consider this face in the primal graph. And let me draw some dual edges. So this face corresponds to this dual vertex, and I'm connecting this dual vertex to its four neighbors, dual vertices. Then if I start at this black vertex. If I reflect this black vertex across this line, I get this white vertex. Then I reflect this white vertex across this line, I get this black vertex. I reflect across this line, I get this white one. And I reflect again, I get back to the original black vertex. What does this mean? It means that the composition of these 4 reflections is actually the identity. Why is that? It's because the composition of 4 reflections is a rotation. Here it's essential that I have an even number of reflections. The composition of an even number of reflections is a rotation. So this is where I'm crucially using that I have a bipartite graph. To have an even number of reflections, I need to have a dual vertex of even degree, which means that my face has even degree. So it's really important here that my graph is bipartite. And so this composition of 4 reflections is a rotation, and since all the lines go through this center, the center of the rotation is this point. And I also told you that this black vertex here is a fixed point of this rotation, which is different from the center, so this rotation has to be the identity. So now let's rephrase this, the fact that we have the identity here. You have a composition of 4 reflections, and you know that when you have a composition of 2 reflections, it's a rotation of angle given by twice the angle between the 2 lines. So the composition of these 4 reflections is a rotation of angle twice the sum of these 2 angles. And since this composition is the identity, it means that the sum of these 2 angles times twice the sum of these 2 angles is 0 modulo 2 pi, so that the sum of these 2 angles is 0 modulo pi. So whenever you start with the circle pattern and you consider only the graph, only the drawing of the dual graph, this drawing has the following property. Around each dual vertex, the sum of every other angle is 0 modulo pi. And actually, you can go the other way. If you start with an arbitrary drawing of the dual graph, then if you have this property that around each dual vertex, the sum of every other angle is 0 modulo pi, then it means that it comes from some circle pattern. So this is summarized here. From now on, all the graphs we will consider will be bipartite. And if you start with a circle pattern, there will be a 2-parameter family of circle patterns with the same centers. And if you start with an arbitrary drawing of the dual graph of G, it corresponds to circle centers for some circle pattern for G, if and only if, around each dual vertex, the sum of every other angle is 0 modulo pi. Here I'm considering only drawings of the dual graph, which may or may not be embeddings. If I require additionally that I have an embedding of the dual graph, then this embedding of the dual graph corresponds to some circle centers, if and only if around each dual vertex, the sum of every other angle is exactly pi. Not 0 mod pi, but pi, let's say modulo 2 pi. Why is that? It's because in your combinatorial graph G, you have some cyclic ordering of the neighbors. Let's say you have a dual vertex 0, you have a cyclic ordering of its 4 neighbors, 1, 2, 3, 4. And when you have an embedding, this cyclic ordering is preserved. But when you don't have an embedding, this cyclic ordering is destroyed. So when you have an embedding like here, you see that the sum of every other angle is strictly between 0 and pi, between 0 and 2 pi. So if it is 0 mod pi, it has to be pi modulo 2 pi. So we can rewrite this sum of these 2 angles in terms of the position in the plane, in the complex plane, of these 5 dual vertices. It's simply the argument of this ratio plus the argument of this ratio. And saying that the sum of these 2 is pi means that this alternating product is negative real. So what is this product here? Let's be careful. It's an alternating product of dual edge vectors, which are all pointing out of the central dual vertex 0. We'll come back to that later. And this condition, you see, sounds like the Castellane condition. Some alternating product which should satisfy some sign condition. And just like in the dimer model, we defined x variables, which are positive numbers associated to each face, we are going to associate to each face here a positive number. How do we do that? We just take, so this is a negative number, we take minus this number. This is a positive real number. Or to put it differently, you can take the modulus of each term, and it's just the alternating product of the dual edge lengths around a given dual vertex. All right, so how much time do I have? 55. Okay. So now let me explain the correspondence between dimer models, part 1, and circle centers, part 2. So we're first going to go in the easier direction from circle centers to dimer edge weights. So we start with some planar graph G, so it's the setting of the second part, and an embedding of the dual graph of G as circle centers. And we want to construct, like in part 1, some complex edge weights for G, which should satisfy the Castellane condition. So how do we do that? Starting from our embedding, whenever we have an edge here between a black vertex and a white vertex, we look at the associated dual edge. And we look at the corresponding vector in the embedding as circle centers. And we orient that vector in such a way that the black vertex lies to the left of the vector. And we assign this complex number to this edge. This is the complex edge weight. So to give you an example, if you have this bipartite graph, then if you want to know the complex edge weight here, it will be this vector here, because you see black lies on its left. And these edge weights actually satisfy the Castellane sign condition because of the remark I made at the very end of part 2. If you look here at a dual vertex of degree 4, then there is actually a phase here in the primal graph. If I take the alternating product of the complex edge weights on this phase, it corresponds to the alternating product of the dual edge vectors around that dual vertex. But this time you see that the orientation of these dual vectors is alternating, in, out, in, out. And I told you previously that when they are all oriented out of this central vertex, then the alternating product is negative. And here, for dual vertex of degree 4, I'm reversing the orientation of 2 edges. So it will still be negative. But here, when I have a dual vertex of degree 6, I'm reverting 3 orientations. So it will become positive. So this is exactly the Castellane sign condition. So starting from an embedding of the dual graph of G as circle centers, I constructed some complex edge weights satisfying the Castellane sign condition. And another property of these complex edge weights is the following. If you look, let's say, at this white vertex, it has 3 edges incident to it, and the sum of the 3 complex edge weights incident to this white vertex is 0. Why? Because they are just given this white vertex here in the dual graph corresponds to a dual face. And each complex edge weight is just one vector, one side of this dual face. And because the dual face is closed, the sum of these 3 vectors is 0. So you see these are very special edge weights. They have 0 sum at each vertex. To put it differently, we can say that these edge weights have 0 divergence. So, yes?
About the boundary.
Yes, so let's forget about the boundary for 5 more minutes. There is an issue with the boundary, and I'm going to explain it in 5 minutes. All right, so this is somehow the guiding principle. It's that there is a correspondence between 2 local conditions for bipartite graph. There's the geometric condition, local condition, being centers of a circle pattern. This local condition is equivalent to the local condition for dimers being Castellane edge weights plus having 0 divergence. So this is not really a theorem, it's more a guiding principle. In order to state something rigorously, we need to take into account the boundary conditions. So there will be statements in the next few slides about that. And the fact that the circle center embeddings satisfy the Castellane condition was also observed independently and around the same time by Affolter. So we started with some circle center embeddings. We had the X variables for them, defined in part 2, and we constructed some complex edge weights, dimer edge weights, and there were also X variables for dimers defined in part 1. And actually, the two notions of X variables coincide under this correspondence. And if you are very classically minded and you like positive edge weights on your dimer graph, then you can obtain them from the circle centers by just taking the modulus of the complex edge weights, which is just the distance between two adjacent centers. It's the dual edge length. Now, let's try to go in the other direction. So, start from a dimer graph with positive row edge weight, and you would like to find some circle center embedding of the graph G, which will give you these edge weights. Actually, it's generally not possible, because I told you that the weights that you get from circle center embeddings sum to 0. So if you take arbitrary weights to start with, they won't sum to 0, so you won't be able to obtain them. But still, you would like these circle centers to be universal. And then you remember, you don't really actually care about the edge weights. What you care about are gauge equivalence classes. So you should rephrase the question, fix edge weights to begin with, and look at the gauge equivalence class of these edge weights. Can you find some complex edge weights coming from circle centers which fall in this gauge equivalent class? If you can find such weights, we will call these complex edge weights a Coulomb gauge, because they have 0 divergence. And the Coulomb gauge in electromagnetism is a choice of gauge such that the vector potential A has 0 divergence, hence the name Coulomb gauge. So, yes. Right, so I should have said that. Once you look at complex edge weights, the notion of gauge equivalence is multiplying by complex lambda, not positive lambda, non-zero complex lambda. So going in this direction from dimer weights to circle centers is much harder, and you need to take into account here rigorously the boundary issues. So let me explain now what is happening with the boundary. Let's look at this graph here. So whenever you have a planar graph, how do you classically define the dual graph? You put one dual vertex inside each bounded face, and how do you deal with the outer face? You usually say, well, it's just a face like any other face, and you place a dual vertex in there. And whenever you have you have an inner face which is adjacent to the outer face, you will connect the two with a dual edge. So here, because you have 4 faces, inner faces which are adjacent to the outer face, you will have 4 dual edges going outside and meeting at the outer dual vertex. But actually, we are going to consider a different notion of dual graph. We are going to prescribe that these 4 dual edges that go out are going to different outer dual vertices. So there will be as many outer dual vertices as there are sides of the boundary. Here there are 4 sides of the boundary, so there are going to be 4 dual vertices, and we are also going to connect with a cycle, a 4 cycle here, these 4 outer dual vertices. And we're going to call this notion, which is less classical than that notion of dual, we will call that the augmented dual of the graph G. And this is the graph which we are going to embed, for which we are going to embed the circle centers. So the statement is the following. Start with a planar graph, which is bipartite and carries positive edge weights. And also technical assumption, assume that the outer face has degree 4. Then you would like to find some circle pattern embedding, circle center embedding of the dual, which are gauge equivalent to the original weights. Do such embeddings exist? Actually, yes, they exist, and there are infinitely many of them. To go down to a finite number, what you should do is to prescribe some boundary conditions. So you should prescribe, you see this 4 cycle in the outer face. you should prescribe where this force cycle goes. So what we're going to do is that we are going to fix a convex quadrilateral P, and we are going to impose that this force cycle goes to this convex quadrilateral. And once we impose that, there are only two embeddings of the augmented duo as circle centers, which will give you gauge equivalent weights to the original weights. So that's the result. And a way to rephrase the result is the following. Instead of starting with a weighted graph, start with an unweighted graph G with boundary length 4. Then, whenever you prescribe the boundary conditions, some convex quadrilateral P, this defines a 2-to-1 correspondence between, on the one hand, embeddings of the augmented duo of G as circle centers, and on the other hand, diameter Boltzmann measures on G. It means that inside each gauge equivalence class, you have exactly two embeddings as circle centers. And so how does the proof go? First, we prove explicitly this result for a simple graph, the force cycle, and then we use induction. We use some local moves to construct any arbitrary graph with boundary length 4 from the force cycle. I will show you in the next part. There are two local moves, one for the diamond model and one for circle patterns, which allow you to construct any graph from this. So the induction step also works when you take boundary length greater than 4. What so far we cannot get to work yet is the base case. We need one graph of boundary length 6 for which we can prove this, and then we would have the result for other boundary lengths. So we expect this result to hold in some form, maybe not 2 solutions, maybe more solutions, but for other boundary lengths. No, it's just, I mean, you know, if we have a boundary length 6, for example, there would be more solutions, maybe 6, and we don't know, we don't have a guess for the number of solutions as a function of the boundary length. Yeah, but here everything is planar, so there's no genus. I don't think so. So this is the case of a finite planar graph. Now we can look at another setting, which are infinite graphs, which are also planar bipartite, which carry positive edge weights, and which are periodic in 2 directions. And the edge weights are also periodic in 2 directions. So here you can look at a fundamental domain of size 2 by 2, and you just repeat this fundamental domain, and you get this infinite graph. So we would like to have a classification also of circle center embeddings. But this time we can't say that they are in correspondence with Boltzmann measures, because there are no Boltzmann measures for the diamond model on infinite graphs. But what replaces the notion of a Boltzmann measure is a notion of a Gibbs measure. So start with an infinite periodic weighted graph G. A Gibbs measure is any probability measure on the space of diamond coverings of this infinite graph, which has the following property. Whenever you fix a finite subset of edges and you condition on the configuration outside of this finite subset, then the conditional probability for the diamond model on this finite subset is nothing but the Boltzmann measure induced by the positive edge weights. And actually, for the diamond model, there is not uniqueness of Gibbs measures. There is a whole convex set of Gibbs measures. And the extremal points of that convex set are called ergodic Gibbs measures. An ergodic Gibbs measure is called liquid if the edge-edge correlations decay polynomially with the distance. So this seems maybe a bit abstract, but actually the way we have a handle on these ergodic Gibbs measures is some result by Kenyon, Okunkoff, and Sheffield, which says the following. Associated to that infinite periodic graph, there is some algebraic curve called the spectral curve of the graph. And when you draw this spectral curve in log-log coordinates, then you have an object called the amoeba, and which looks like this. And the interior points of the amoeba are in one-to-one correspondence with these liquid ergodic Gibbs measures. And the way actually we define the spectral curve is by using some deformation of the Castellane matrix. So this is how we manage to work with these objects. So in this case, the result is the following. You start with an infinite infinite graph periodic in two directions with edge weights. Yes. Yes, it's log of the modulus of z, right? You start with an infinite graph, which is periodic in two directions and carries positive edge weights. And you want to find some circle center embeddings which are periodic, meaning that the drawing has to be periodic. When you go from one fundamental domain to the next one to the right, there should be a translation by some fixed vector u. And when you go to the next fundamental domain above, there should be a translation by a fixed vector v. You are looking for periodic circle center embeddings of the dual, which will produce complex edge weights which are gauge equivalent to the original ones. Is it possible? So yes, it is possible. There are infinitely many possibilities, and these possibilities are in one-to-one correspondence with the liquid ergodic Gibbs measures on this graph G. Yes? Sorry? Can you speak?
Where are the probabilities for your circle patterns?
There are no probabilities. It's a correspondence between weighted graphs and circle patterns somehow. If you want, I mean, you can forget about the ergodic Gibbs measures and just think about points on the amoeba. These are values of z and w such that k of zw is singular. So yeah, this is something we would like to have, an interpretation of the probability that an edge is present in the dimer configuration in terms of some geometric quantity, some angle or whatever, in the circle center embedding. This is something we don't have yet, but it would be nice to have something like that. And so here I would like to stress something about the two directions, going from dimers to circle centers or from circle centers to dimers. The hard direction is to go from dimers to circle centers. If I give you a dimer graph, whether finite or infinite, and you want to construct the associated circle center embedding, there is no local construction, meaning that if you just care about constructing a few circles, you still need to know the entire edge weights on the entire graph to be able to do that. So it's a global construction, and that's why it's tough. But by contrast, if you start from a circle pattern and you want to construct dimer edge weights, then it's a local construction. What is the edge weight on a given edge? It's just the length of the associated dual edge. So these circle center embeddings somehow give you some nice gauge where everything becomes local. It's hard to find this gauge. It depends globally on the edge weights, but once you are in this gauge, everything becomes nice. So 10 minutes? Okay. So now let me discuss two local moves, one for the dimer model and one for circle pattern, which are actually equivalent and which produce two integrable systems. So for the dimer model, it's a move that actually already appeared in Sunil's talk. Let me forget about the contraction of degree 2 vertices because I don't have much time. Let me just discuss about the urban renewal. Whenever in your dimer graph you have a face of degree 4 with these edge weights, you can erase these 4 edges and replace them by these 8 edges with different edge weights. And when you do that, and when you look at the correlations between edges that are away from the place where you did your urban renewal, this will not change the edge correlations. So these are local moves that preserve the probabilistic model. And if you want to see how the x variables, which are the actual coordinates on the space of Boltzmann measures, evolve on the urban renewal, they are given by these formulas. So you see there are very simple, rational formulas in the x variables. And actually they are extremely nice because these are some mutation rules for coefficient variables in cluster algebras. So it would take me 1 hour to explain what a cluster algebra is, but somehow it's some structure which is ubiquitous in many discrete integrable systems. So it is nice to have this connection observed by Goncharov and Kenyon between local moves for dimers and cluster algebras. Sorry? So what can I take from the theory of cluster algebras to deduce? So for example, when you have a cluster algebra structure like this, you automatically have a Poisson bracket on your space. This is work of Gekman, Shapiro, and Weinstein. So for example, it will give you some natural Poisson bracket on the space of edge weights modulo gauge. And this Poisson bracket will allow you to formulate the Arnold-Liouville integrability for the diamond integrable system. This is something you get for free, for example, this Poisson structure. Integrability somehow means that I have some dynamical system which becomes linear in certain nice coordinates. It's like in Terence's talk yesterday. You have a way to linearize this dynamics. There are many meanings actually of integrability, and the diamond model is integrable in many of these definitions. But here, by integrability, I meant making the dynamics linear on a torus. What? I mean, the fact that the system is linear on a torus is already nice. You can use these urban renewals to compute partition functions, for example, of the Aztec diamond, but it's not what the direction in which I'm going here. But you can do it. So these are the local moves for the diamond model, and similarly, you have local moves for circles. Actually, you have two levels. You have local moves for circle centers and for the higher level of circle patterns. Let me skip again the contraction of degree 2 vertices to go to the interesting one, the analog of the urban renewal in the case of circles. It is based on Michel's theorem, which says the following. Suppose you start with a chain of 4 circles, north, west, south, and east. North and west intersect in 2 points, AA prime, west and south in BB prime, south and east in CC prime, and east and north in DD prime. Then Michel tells you that 4 of these points, A, B, C, and D, are concyclic, meaning that there is a circle going through these 4 points, if and only if the other 4 points are concyclic. You can rephrase this like that. Suppose you start with 5 circles in this configuration, then there is a map from these 5 circles which produces a 6th circle. And then you can ask the question, because we are interested in circle centers. Suppose I only start with the data of the 5 circle centers. This is less data than the 5 circles. Can I, from this data, derive the position of the 6th circle? It's not obvious, because maybe you know there are another 5 circles which have the same centers, but which will produce another 6th circle with a different center. So it's not obvious that something like this holds, but actually it is true, and there is even a very simple formula. So if you give names like this, complex, these are the position in the complex plane of these centers, north, west, south, and east, and the 5th circle has position C, the 6th one has position C prime, then these 6 complex numbers are related by this relation. This is somehow we revisited Michel's theorem 180 years after. Michel looked at the circles and we looked at the centers. And there's also something nice occurring with the centers. As you see, this equation, the numerator is linear in C prime and the denominator is linear in C prime, so you can express C prime as a function of the other 5 centers. And so this is actually a well-known equation in discrete integrable system, but I'm going to skip this, and you can use Michel's theorem to define the Michel move for circles and the Michel move for centers. So for circles, it means that if you start with this configuration of 5 circles, you can erase the central circle and replace it by the other, the 6th one. And Mikhail move for centers, you just forget about the circles, and if you start from 5 centers, you can erase the 5th one and replace it by the 6th one, like this. And again, if you look at the circle pattern X variables, the way they evolve under this Mikhail move is using these equations, which are exactly the same as the ones that you had for the urban renewal. So actually we can identify the Mikhail move with the urban renewal. Under the dimer circle correspondence, these two local moves are the same. So, how much time left? 3? 4 minutes? Okay, so you can use these local moves to define some discrete time dynamical systems. So since I already, thanks to your question, briefly mentioned it, I'm going to skip it. These are some discrete time dynamics which become linear once you take nice coordinates. So you have one for dimers, and you have the same one for circle patterns. And because Goncharov and Kenyon proved that the dynamics for dimers is integrable, we know now that the dynamics for dimers is the same as the one for circle patterns, it automatically entails that the one for circle patterns is integrable. And actually, I should say that this was one of my original motivations to study the dimer circle correspondence. I was working on this Mikhail dynamics, the dynamics for circle patterns, and I wanted to show it was integrable. And the way to show it is to use this correspondence, actually. So very briefly, some perspectives. To go back to the original slide, we've been studying this dimer circle correspondence mainly in the direction of integrable systems. But it would be nice, actually, to also use this correspondence to derive results about the dimer model in statistical mechanics, like the question you ask, can you interpret edge probabilities in a geometric way? And so the connection between graph embeddings and statistical mechanics is very old. Whenever you have some statistical mechanical model, it is usually not defined on an embedded graph, but just on a graph without an embedding. But whenever you are looking at some scaling limit questions, you need to consider a specific embedding of your graph. So this is a very important question, and it arises for every model to find some appropriate embedding in which you can phrase the scaling limit result. And it also holds for some random maps questions, scaling limits of random maps. And so very briefly, what could we expect from this dimer circles correspondence? So maybe some local formulas for the correlation. So you know, if you have 2 edges in your dimer graph, the correlations between these 2 edges depend globally on all the edge weights of the graph. But maybe once you are using some nice embedding, you only need to know the local geometric information to compute these correlations. Why would such a miracle occur? It's because the local geometric information actually captures the global combinatorial information already, because there was this map from dimers to circle, which was global. But once you have this nice embedding, maybe everything becomes local. So there have already been several results for several models, special cases of the dimer model, special cases of the Ising model, the spanning tree model by various people. And the other kind of results one could hope to get are limit shape results. So there are already many results about limit shapes for the dimer model, but we could maybe try to have some systematic machinery for it. So this is I think Sunil presented some limit shape in his talks. So this is some limit shape for the dimer model for the Aztec diamond. And last slide. Why is it reasonable to expect that? So I introduced some embedding, circle center embedding. Why is it reasonable to expect that this embedding is the right one in some way for the dimer model? So first, because we have some local move on the geometric side, which is compatible with the dimer local move. Second, because as you remarked, there is already a correspondence between a certain subvariety of dimer weights and certain subvariety of circle patterns. The circle patterns where all the radii are equal. These are called isoradial circle patterns. And the locality results that I mentioned on the previous slide hold for isoradial in the isoradio case. So maybe one could extend them. And also there is some ongoing work on the statistical mechanical side, study of these embeddings by Čelkák, Lallier, and Ruskir in an upcoming paper, where they define the good notion of discrete holomorphic functions on such circle center embeddings. And finally, reason to think that these embeddings are the appropriate ones to study the diamond model is because we know two embeddings already, the TOT embedding associated with the spanning tree model, which is adapted to the spanning tree model, and Čelkák recently introduced the S embeddings, which are adapted to the Ising model. He can prove some scaling limit results for the Ising model using S embeddings. And actually, there's a reduction of both the spanning tree model and the Ising model to some bipartite diamond model. And under this reduction, actually, the S embeddings and the TOT embeddings become special cases of circle center embedding. So the circle center embeddings generalize the TOT embedding and the S embedding. And I will stop here. Thanks for your attention.